Okay, so this video will go over exam 2 study guide. Exam 2 is on chapter 4, 5, and 7. So the first page of the study guide and the study guide is available on Canvas under the exam module. So you need to look for the exam module. I think that module is just below chapter 7 module. And you will find there under the heading exam 2, study guide for exam 2. And there are things reminded here, but that's more for, ionic compound, like, the cation charge is equal to the group number for group 1A, 2A, and 3A. The anion charge is 8 minus the group number for nonmetals. These are not as needed in this, well, let me think. Well, for chapter 5, it's still good to know how to find the formulas of ions. But one thing you want to remember well is that the number of valence electrons, and that's needed for when you are doing Lewis structures, for example, it's the group number, right, for all A groups. And then you want to be aware of the bonding patterns for common main group elements, like hydrogen only makes one single bond. Carbon typically makes 4 single bonds. Nitrogen makes 3 single bonds, or one double, one single, and then has a lone pair. And oxygen typically makes 2 bonds and has 2 lone pairs. And then the halogens, they are what we call peripheral atoms. They typically make a single bond and have 3 lone pairs around them. So you want to be aware of those bonding patterns, to have the correct Lewis structure. So these are the recommended end of chapter problems. If you have the textbook, the Smith General Organic and Biological Chemistry from Smith. So anyway, we'll go over the learning objectives for chapter 4, 5, and 7. So in chapter 4 is all about covalent compound. And covalent compound are also called molecular compound, because when you have compounds made with covalent bonds, we call them molecules. And so you want to remember the difference between ionic and covalent bonds. And so in covalent bonds, electrons are shared between atoms and sometimes unequally shared. And so that's why you have polar bonds. But if electrons are shared equally, it's pure covalent bonds. In ionic bonds, the electrons are transferred from the metal to the non-metal. Right? That's also a difference between ionic and covalent, is that covalent compounds are made of non-metals only. And if, for example, you forgot, then you can always go to the reference here. So that's the reference information. And if you go to the very last page, so this is good to have under your eyes here the names and formula of common polyatomic ions. And then this page with electronegativities, electronegativity difference, and then the type of bonds. That's important for chapter 4. Lewis structures, know how to use this table to find the shape of the molecule. And then, so that's chapter 9. And then here, the flow chart here reminds you that ionic compounds are made of a metal and non-metal, and molecular compounds, which are also covalent compounds, are made of non-metals only. And we have learned how to name them only when we have 2 non-metals. So you name the first non-metal first, using a prefix for the number of atoms, using those prefixes here. Depending on the number of atoms, except you don't use mono for the first non-metal. And then the second non-metal should have the ending of its name and to hide. So here it reminds you, what molecular compounds are made of. So recognize the bonding characteristics of covalent compounds. We just discussed that. So the main thing is that you need to be able to draw Lewis structures, and including resonance structures if applicable. Yeah, I actually will not, really look for that, but so for this, you need to be structured. First, you count the total number of valence electrons that are available to distribute in your Lewis structure. And remember, the number of valence electrons for each atom is the group number for those A group elements. And that's the case for all nonmetals. And so you have your total number of valence electrons. Then you position your atoms such that typically the first element in the formula is the central atom. And you also want to make symmetrical molecules. And then you start distributing your single bonds and removing the number of electrons you used to make your single bonds. You remove that from your total number of valence electrons. And then you will do the octet for the outside atoms first. So octet means you want 8 valence electrons around each atom. So you do your lone pairs on the outside atoms. And if you have still enough atoms, you can then do the octet on the central atom. But if you don't have any more electrons, that's when you need to share a lone pair from an outside atom to a central atom. So how do we check that we have a correct Lewis structure? You want the correct number of valence electrons, in the structure. So the total number of electrons should be the one you calculated. And you want each atom to have an octet. So that's the 2 things you need to check to get the correct Lewis structure. Name, we've just seen that earlier. Predict the shape. So to predict the shape around an atom, and so let's look at all of this with the reference packet. Use electronegativity to decide if a bond is polar or not, and then determine the molecule polarity. We'll all use that page of the reference. So you want to have page 4. For most of the references is page 4. So here you want to be able to use the electronegativity values to calculate the electronegativity difference between 2 atoms, the 2 atoms that are bonded. For example, if you have C bonded to O and then O bonded to H, you need to do the OH bond and then the CO bond. There's no need to do the electronegativity difference between atoms that are not bonded. And so, and also it doesn't matter that it's a triple bond, a double bond, or a single bond. The electronegativity difference will be the same. And so the electronegativity difference should be a positive value. So always place the higher value first minus the smaller value. And so using that electronegativity difference, and using the middle table here, you're able to classify your bonds as polar or non-polar. When you have covalent compound, it's going to be the first case or the second case. When you have a electronegativity difference greater than 1.9, then it's an ionic compound. But in this exam, we are not testing on ionic compounds. So, so if your electronegativity difference is less than 0.5, which means up to 0.4, then it's non-polar. And typically, the CH bond, for example, is non-polar. And then when it's 0.5 up to 1.9, then it's considered polar, which means electrons are unequally shared between the atoms, and the atom that is more electronegative is pulling the electrons towards himself. And then once you have your Lewis structure, you use this table to find out the shape. So you have to be very careful. Here there is electron geometry and molecular geometry. But when we are talking about the shape of the molecule, it's the molecular geometry you should read, right? Make sure you go all the way to molecular geometry to record the shape of the molecule. So it starts by counting the number of electron groups. And here, if you look at the little sentence at the bottom of the table, it says, count only electron groups around the central atom, right? You need to focus on the central atom. And each of the following is considered one electron group. So one lone pair is an electron group, a single bond, a double bond, and a triple bond. They each are considered one electron group. So it doesn't matter that you have a triple bond or a double bond, you count it as one group. Right, so that's why it's up to 4 groups around the central atom. And then depending on the number of bonding groups and the number of lone pairs, then the shape changes. Okay, so that's how you would do find the shape. Let me go back to the study guide. Okay. Do you have questions on chapter 4? Okay. So chapter 5, so that's really a big chunk here. That's where you learn to write chemical equations. And so write them and then balance them. So balancing is necessary because it satisfies the law of conservation of mass, which means you will have this, by balancing, you will have the same mass on the left side of the arrow than on the right side of the arrow. The arrow symbolizes a chemical reaction or chemical change. So you need to be able to classify chemical reactions as combination, decomposition, single replacement, or double replacement. So it's good to have a generic form for each. So yeah, I should have opened my, let me, hold on. Yes, so here a combination reaction is typical in the way that it has only one product, right? So you have 2 or more reactants and they form only one product. You're combining them to synthesize a bigger molecule. Decomposition is when you have one reactant only and you're breaking it into 2 or more products. So it's the reverse of the combination. Single replacement is when you have an element and a compound, and there will be a exchange of one of the atom, and so you will form a new compound and the element will be different. So a new compound and a new element. And then a double replacement reaction is when you have 2 compounds. Typically it's for ionic compounds that works, and it's very it's easier to see with ionic compounds than covalent compound. And so the 2 compounds will exchange partners or exchange ions in the case of ionic compound and make new compounds. And so these double replacement reactions are often precipitation reactions. If you are mixing 2 solutions of ionic compound that are soluble in solution, when you're mixing them and and one of the product will be a solid, one of the new compound is a solid, then that's a precipitation reaction. Acid base also are double replacement reaction. You can see that here. The acid will give H plus, and then the base will give an OH minus, and they will combine together to make H2O, the water. And then the cation from the base will go with the anion from the acid to make the salt MX. So acid base are also double replacement reaction. We will study acid base more in chapter 9. But combustion, that's something I really want you to recognize. A combustion reaction is when you have a compound made of carbon and hydrogen, and sometimes there is oxygen in the compound. And when you are burning it with oxygen from the air, so oxygen is part of the reactants, and you're making carbon dioxide and water, and it's all in gas phases here because you're burning, so it's high temperatures, so that's why they are as gases, they escape as gases. This is a combustion reaction, and I want you to really recognize that type of reaction. So these combustion reactions are exothermic. They release a lot of energy, and that's why we use them. And so the thing that we burn are, you know, all those fossil fuels, wood, wax, you know, gasoline, kerosene, all these things that we are burning to get energy. So we are using combustion reactions a lot. Let me go back to the, did I? Study guide. Okay, so that's the points where you need to recognize combustion, precipitation, and acid-base reactions. Oxidation reduction reactions are when there is a transfer of electron from an element to another. And out of these, we ask that you recognize the compound that or the element that is being reduced and the element that is being oxidized. You practice that a little bit with the lab 4. Okay, and then the second part of the chapter 5, you know, is on calculations that use the mole. The mole is, by definition, equal to 6.022 times 10 to the 23rd number of particles, right? And you need to use that as a conversion factor because it's an equality between the mole and the Avogadro number of particles. And so to talk about the rest of what's listed here, I'll go back to the reference packet. Where's the reference? What did I do with my reference? Hold on. So for chapter 5, this is the reference packet. And for chapter 5, you want to use that page 2 of the reference packet. That's where all the information for, you know, the second part of chapter 5 is there, you know. So there is the Avogadro number definition of the mole here. So 1 mole is 6.022 10 to the 23rd particles. And so whenever you need to calculate a number of molecules, atoms, or, you know, formula units, then you will change particles with the corresponding particle you have. And you can use that as a conversion factor. And so there are two types of roadmap, depending on if you're dealing with just one substance. And so that's going to be using the first roadmap here. If you're dealing with just a substance and you have grams of it, for example, and you want to find the number of particles there is in that mass, then you will use the first roadmap starting from the right with grams of A. And then you will use the molar mass of A to change that into moles of A. So how to get the molar mass? It's from the periodic table, right? Let me. The molar mass is those numbers below the names of the elements, with decimals. That's the molar mass in grams per mole. So for example, the molar mass of CO2, you would take 1 time the molar mass of C plus 2 times the molar mass of O. So 1 times 12.01 plus 2 times 16.00 equals 44.01 for CO2, right? So that's how you get the molar mass of compounds. It's by adding the molar mass of each element and multiplying by the subscript for that element, and then take the sum of all of these contributions. So the molar mass is very useful. It allows you to change grams to moles, or, if you have moles, to retrieve the mass of that substance. So here you would, if you have grams of A, you would use the molar mass to get moles of A. And then if you need the number of particles of A, then you would use the Avogadro number, which is the definition of the mole above here. So you would use that to find the number of particles. And of course, this roadmap can be used from left to right, from right to left, and you can only do one step in not the two conversions, right? So it's just a guide here. And so then the other type of calculations are involving two substances that are related by a balanced equation. So let's say you have a balanced equation, and here that would be the, formula A plus formula D gives B plus C, and then the W, X, Y, and Z are coefficients, right? The coefficients to balance the equation. And so let's say the question of a text, for example, is talking about substance A and B, for example. A is a reactant, B is a product in this case, but it doesn't matter, right? It could be involving two reactants or two products. It doesn't really matter. And so if, for example, you're given grams of A, and the question is asking how many grams of B will be produced from this mass of A, then you would have to do 3 conversion factors, multiply your given amount by 3 conversion factors. Each arrow between the labels there are conversion factors. So because the substance A and B are related in moles, in number of moles from the coefficient of the equation here, you can only change the moles of A to moles of B using the coefficient from the balanced equation, right? So that means whenever you have mass, you need to change it to moles. You need first to change the grams into moles using the molar mass of A. You adapt the molar mass to the substance in question. Then you are able to change your moles of A to moles of B using the coefficient from the equation. And after that, moles of B, to get back to grams of B, you use the molar mass of B. So this roadmap here, shows the full calculation when, you're asked a mass of a substance from the mass of another substance. But of course, the question could ask for moles given a number of grams, or you could start with moles of A and be asked grams of B, right? You could start at moles of A instead of grams of A. And also, the question can simply be, how many moles of B are produced from this number of moles of A, right? It could be just one step, and that could be that middle step. And there is this example below here to show what it looks like, right? If you have reactant grams, that's your given amount. 1 reactant mole over reactant grams is the molar mass of that reactant. And then you change the reactant moles into into moles of product. So this middle conversion factor is using the coefficient from the equation, and then you use the molar mass of the product to find the grams of the product. Another thing in chapter 5 is calculate the percentage yield that is produced. And for this, you would need to be given the actual yield of a product made and over the theoretical yield. And the theoretical yield is the one that you obtain by doing the calculation like above here, where you use the molar mass, the proportions given by the equation, and then using the molar mass again. It's the, in theory, what you should get, right? But very often the amounts we get are smaller. So that's why we have an actual yield that is usually smaller than the theoretical yield. So times 100, and that tells you how much actually you got, of the product. Yeah, that makes me think when you are looking for the limiting reactant, you need to compare. So yeah, that's honestly, I don't ask for that in the exam, so I don't want to spend too much time on this. But like in your quiz, you had a question like that, to determine the limiting reactant. And the limiting reactant is the reactant that will limit the amount of product that can be made. It will be completely used up, and you cannot make more product because it's all gone. So you want to find how much product you can make from each amount of reactant you have, and then compare the amount of product they make. And the smaller amount indicates, the limiting reactant. Sorry, it's kind of hard to explain with just with nothing in front to show an example of that. Okay, and then chapter 7, there is it goes over again the states of matter, gas, liquid, and solids. It's good to have a mental picture of what they look like. Right, it's good to have a mental picture of what gases, liquids, and solids look like. And so gases are free from each other. The particles are free from each other, flying around. They are not attracted to each other. And the higher the temperature and the faster they move, because the more kinetic energy they have. The liquid, the particles in the liquid are packed together like in the solid, but in the liquid phase it's random, there is no order. And in the solid phase it's ordered, right? So that's how we recognize them, at the atomic level. Let me go back to the study guide here. So how the effect of intermolecular forces on why do you have a gas, a liquid, or a solid? And so what keeps the molecules packed together and ordered in the solid phase are intermolecular attractive forces, right? As the name says, intermolecular, it's forces. Inter means between, so it's forces that act between molecules of a substance, right? And so it keeps the molecules tightly together. And so they will be strong in the case of a solid. And those intermolecular forces will be non-existent in the gas phase, right? And in the liquid phase, they will be moderate. And you have to balance that with the amount of kinetic energy. So a gas will have a lot of kinetic energy versus a solid will have very little kinetic energy. And that's how, that's what determines if you have a liquid, solid, or a gas at room temperature. So gases, the kinetic molecular theory, tells you that, it's made of small particles that fly around, that are far from each other. There's a lot of distance between the particles, no attractions between them. And then the speed of the molecule will depend on the temperature. So that's what the theory, tells you. You need to be able to change pressure from a unit to another, and then use all these gas law, the molar volume that says 1 mole of any gas is 22.4 liters at STP. The ideal gas law, P times V equals nRT, and the Dalton's law of partial pressure. The total pressure of a mixture is equal to the sum of the partial pressures of each gas in there. Let me go back to the reference. And so for chapter 7, it's the first page of the reference that you want to have on hand. Because here you have the pressure units. It tells you how 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 14.7 psi, which is also equal to 101,325 Pascal. So all of these are equal together, right? It's not just atmosphere with millimeters of mercury, it's atmosphere with psi, pascals with psi, or pascals with millimeters of mercury, right? Standard pressure and temperature are these values. Typically, what it's useful to know, it's that you are at STP, like here. When you are at STP, that allows you to use the molar volume, and that usually what this is useful for. It tells you that you are in the conditions where you can use this relationship here between 1 mole of any gas and the volume of the gas, 22.4 liters. Combined gas law, we don't, we didn't go over this, so should remove that. The ideal gas law, so pressure times volume is equals the number of moles times R times T. And R, you will choose the value depending on if your pressure is in atmosphere or millimeters of mercury. And these are unit, the units of liters times atmosphere per mole and per Kelvin, reminds you that, volume has to be in liters, temperature has to be in Kelvin, number of moles has to be in moles, and then you adapt the R value. If you have atmospheres, you would use the first one. If you have millimeters of mercury, you would use the second one. And so change your pressure unit if needed. And then Dalton's law of partial pressure. That says, the partial pressure of each gas in the mixture, when you add them, they will give you the total pressure of that mixture. So then the chapter 7, most of it is on intermolecular attractive forces. That thing that is, the acronym is IMF, intermolecular forces. I tend to say attractive in between, but here in the acronym there is not the attractive. I said attractive because it's forces of attractions, right, that keep molecules together. And so there is the London dispersion forces, which all molecule experiences. So you should always list that one when you're asked, what are the intermolecular forces between the molecules of a substance. You should always list London dispersion forces. Dipole-dipole interactions only occur between molecules that are polar. So you need, because dipole here refers to polarity, so you need molecules that are polar for this to happen, right? And then hydrogen bonding is even more restricted because it only occurs between the hydrogen of a molecule that is bonded to oxygen, nitrogen, or fluorine, and it will be attracted to the oxygen, nitrogen, or fluorine of another molecule. So that's very specific, right? So the hydrogen bonding is the strongest of those three forces. Dipole-dipole is moderate, and then the London dispersion forces are the weakest. So sometimes you are asked to put them in order, or to understand which molecule will experience the strongest intermolecular forces. And why it's important? It's because those forces, they will determine, you know, your boiling point and melting point. And so the stronger the molecules are held together, the more energy it requires to reach the boiling point or the melting point. So that will increase the boiling point and the melting point if the forces are very strong between the molecules of a substance. So when you compare two substances, the one that has the strongest IMF will have the higher boiling point. And be careful, for the vapor pressure, it's the reverse. It's the molecule that has the weakest intermolecular attractive forces that will have a higher vapor pressure. Because vapor pressure is the, you know, above a liquid, you have that gas phase, and we call that the vapor pressure. And so you have more chances of having molecules in the gas phase above the liquid if the liquid is not held very tightly together, right? If molecules are not held tightly together, then more molecules can break free and be in the gas phase above the liquid. Then specific heat and heat gained or lost by a substance. This is this formula. Q is the heat is equal to M times the temperature change times the specific heat of the substance. Yeah, I don't want to spend too much time on that, but know how to use this formula given the values. So phase change, it's important to be able to name them. I noticed that students don't realize they need to know those names of, and let me go back to that here. Here you need to know those names of condensation, deposition, evaporation or vaporization, freezing, sublimation, and melting. You know, you need to know these names and, you know, to what they mean, right? Melting is, you know, going from a solid to a liquid. Sublimation, it's one you probably have not heard a lot, but it's going from a solid to a gas. Freezing, from a liquid to a solid. Evaporation, that's easier. Deposition, going from a gas to a solid without going through the liquid phase. And then condensation, from a gas to a liquid. Another thing is that you want to be able to tell if they are exothermic or endothermic, right? And so the general idea is that when you go from a very organized state to a less organized state, so for example, from solid to liquid, this will be this will be endothermic. You will need to provide energy to break these attractions that hold the molecules together in the solid phase, right? So you need to break those intermolecular attractive forces, and so you need to bring energy to break those attractions so that the liquid, you know, can be more free to move, and will have more kinetic energy because it can move more, right? And then it's going to be exothermic when you go from a very disorganized state to an organized state, because you stabilize the substance by, you know, organizing it and packing it together. It stabilizes the molecule, so this releases heat to the outside, so it's exothermic. Yeah, and then be able to navigate a heating or cooling curve. And there was an example here. I should stay here. Here, to be able to understand this type of curve that shows what happens to the temperature of a substance and also to its phase when you decrease the temperature and remove heat. For example, here it's a cooling curve, but understand what happens when it's a heating curve, when you're adding heat and then the temperature increases. So it's important to realize that while you have reached the condensation point or boiling point here, you have the two phases, and during that time the temperature cannot change. During condensation and freezing or melting and boiling, the temperature is stable, and you have all the way until you have only one of the phase, right? As long as you have two of the phases, the temperature is stable. Okay, so